Welcome to this video on Coulomb's law, which is the law that describes the force of attraction or repulsion between charged particles. So we set up our lab to figure out how strongly are these two opposite charges attracting one another, or how strongly are two like charges repelling one another. And we established that those should be the same law because they're both describing a force between two charged particles. Now, the first thing we want to keep in mind that's very important, I'm going to say this right off the bat, is that Newton's third law is still at play here, right? And the third law means that both of these pull on each other with the same magnitude of force, or push away from each other at the same magnitude of force. So that's an important point that we need to keep in mind the whole time. So we're not going to say that one charge is pulling harder on the other, even if this charge, say, is 4 coulombs and this one's only 1 coulomb. They still pull on each other by the same amount. Now, what we did was we set out to do two different experiments. And the first experiment we set up where we were testing the electrostatic force, right, as a function of the product of the charges. Okay, so that would be Q1 times Q2. All right, and in this experiment, the things that we held constant was the separation distance. Okay, so that was important. Separation distance. In the next experiment, now I'm drawing them side by side. They don't go with the pictures up here. They go independently of that. So in this experiment, we were looking at how does the electrostatic force respond to changes in the separation distance. And in this case, what we held constant was the product of the charges. Okay, so the first thing I'm going to do here is I need to put units for, or put symbols for what each thing is. So Fe, electrostatic force, that's the same. Product of the charges is going to be Q1 times Q2, and we designated that as being an absolute value. Separation distance is going to be R. So go ahead and write those in here. Going to keep the same color code. All right, and then we collect the data. Okay, so in this experiment, one of the charges would be changed, or both could be changed. It doesn't matter, but the separation distance was held constant, and we measured the value of the force and did the same thing here, except varied the separation distance. So I'm going to go ahead and put in two XY planes for us. So here's one of them, and here's the other one. Okay, and let's take a look at what the data showed. So if you did your experiment correctly, what we should have seen was on the Fe versus Q1 times Q2 graph, okay, and remember that this is an absolute value, okay, what we got was a direct proportion. All right, so something that followed y equals mx. Okay, in the experiment of Fe versus R, what we got was something inverse like this, and it actually turned out to be y equals kx to the negative 2, or y equals k over x squared. Okay, and that I got that information from using Excel or LoggerPro. Now this one doesn't need to be linearized because it's already linear, but I'm going to change the variables to Fe equals some number times this product. Okay, and I'm going to go ahead and write those in, Q1 times Q2. Okay, and then on this side over here, we actually had to do some linearizing first. And so if you were going to linearize this graph, what you would linearize it to is, let me go ahead and put the new axes on here. I would go ahead and linearize this to Fe versus 1 over r squared, right? Because it came out as that proportion. And then that should give me a slope. So then my equation on this one is y equals m x, right? Where where y is Fe, m some number, and x is 1 over r squared. Okay, now let's figure out what the slopes represent. Well, remember we talked about this several times, is that the slope, which is the constant parameter of the function, has to line up with the constant that was physical in the experiment. So the separation distance is somewhere in this slope. Over here, similarly, the constant parameter of the function has to match up in some way with the constant parameter in the experiment over here. All right, so if we take that, all right, so I'm going to take this slope. I'm going to say that the slope somehow includes 1 over r squared. Okay, and remember, it has to still maintain the same relationship, so it wouldn't just be r squared in the numerator. In this experiment, we know that the slope must include the product of the two charges, q1 times q2. Okay, this will always be true for any quantitative experiment that you do. Okay, now it's not the only thing that's in the slope, it just includes that. So what we could do then is do multiple trials of different q1 or q1 times q2 over r squared, right? And I'm going to go ahead and graph kind of like a mega linearization. Okay, so we'll do it over here. And this mega linearization is going to be Fe versus q1 times q2 over r squared. So basically what I'm going to do is change, q1, let's say, and get my same data, but pull the r squared now out of the slope and graph that. And I could do it for multiple different variations. And what I see is that the slope comes out to be linear, meaning that there's some other fundamental constant that is included in this relationship. Because no matter what combination of q1, q2, and r squared I had, as long as they related to one another with Fe, it always comes out to be the same value. And that value came out to be 9, sorry, I guess let me write it in scientific notation. So 9 times 10 to the 9th, or 9 billion. Okay, and this is the constant that we're going to call K, known as Coulomb's constant. Now this turns out not to be a universal constant actually, but for right now it's the constant we're going to use, and in later videos we'll see how that plays out. So if I write my function now based on this graph, which is in the basic form y equals mx, where y is Fe, x is all that jazz over there, q1 times q2 over r squared, so that's all my x, and the slope is this constant k. And so what I have established now is what's known as Coulomb's law. And Coulomb's law describes two charges separated by some distance r. If I perform the operation shown here, I should find the number of newtons of attraction or repulsion that those two objects exert on one another. So it's pretty easy to solve for the combination of these things. And it looks very similar to the gravitational field force equation, that is the universal constant times m1 times m2 over r squared, which would be the attractive force for two masses, whereas this could be the repulsive or the attractive force between two charges. So we'll practice a little plug and chug with this formula just to familiarize ourselves with it. But then in another video, we'll take a look at how the force is a vector, and that if I had more than just two forces, two charges pulling on each other, if I put a third in there, how could both affect one or the others? So we'll take a look at that in a subsequent video. So familiarize yourself with the equation, but you do not need to memorize it because it is given on the equation sheets.